So in the thermosphere, I don't remember from 14 years ago. In the thermosphere, which is above the stratosphere, presumably you've had this more recently than I have. You have a whole lot of energy there because the sun radiation comes in, hits the particles in that atmosphere, and those things go zipping around. So we've got the charts that I've seen talk about how high the temperature is. It's got a high temperature just because the particles that are up there have so much energy. However, if you were stepped out into the thermosphere, you would not burn, even though it says 1,000 Kelvin, 1,000 degrees Celsius, whatever the number is. It's hot, but only because the energy is high, not because you got a lot of it there. You don't have much, but what you do have is zipping around fast.
So it's warm because the molecules are zipping around fast and not because of the sun's radiation? Or?
Right.
Okay.
Now, if you stepped out and I guess I was picturing, wasn't worried about the sun.
Mm-hmm.
So the sun's radiation would hit you and then you would warm up from that.
Yeah, from that. But
Yeah.
in that, it's because the molecules are moving.
Yeah.
Okay.
They talk about how high temperature it is up there, and to me that's misleading. Because it's a high amount of energy, but energy and temperature are related.
Okay. That makes sense.
What I want to do now is figure out when we're going to have the quiz on chapters 6 and 7. That sounds like a fun thing to do. I can see that look of excitement. Today is the 11th. How's the 18th grade? Homework
that-
quiz on chapters 6 and 7.
That's next Tuesday?
Yep.
Okay.
So homework quiz on 6 and 7. Again, that's going to be based upon the assigned problems. Now, master set 6 and 7. I think it's master set 6 and master set 7. It's two different master sets. Why don't we say one of them is due on Thursday and the other one is due the 25th. Unless there's some objection at the moment. Need another piece of paper,
Mm-hmm.
and then squeeze in here the 25. Master set 7. So the 20, so the 8, oops, that should be the 20th. All right, so March 18th, homework quiz 6 and 7, based on the textbook problems. Thursday after that, we have master set 6 due, and then the following Tuesday, master set 7. And let me write this down here before I forget. So the 18th says 1, 2, quiz 6 and 7, and then 10 master set 6, 25, master set 7. I think I started this up again, did I? Yep. Questions at the moment? Yes?
The second equation is what you would add to it. Would that just cancel out every time?
Yeah, because it's 0, anything times 0 is 0. So this goes away each time.
Okay.
I typically wouldn't write it in there because I know it has no kinetic energy because it's not moving. These are not moving. But Monica threw it in there, so I thought, oh, let's just do it. It's her fault.
It's my fault. So when you would use that half of the equation is if both balls were moving?
Yeah, in a nice ideal situation, this happens, but in reality, if I swing one back, it is moving some.
And it,
So it's not a perfectly elastic collision.
oh, okay.
It is what I refer to as an imperfect collision. They're not sticking together,
Yeah,
but it's not ideal.
okay.
In terms of names, you just hit that. This is, because I think it shows up in the master set. So if I have a collision, you got momentum conserved, and then you throw in this, what happens with kinetic energy? So, collision types. Or I guess names. So if the initial kinetic energy is the total final kinetic energy is conserved. I want to explain why I call it what I do. Naming convention number 1 calls this a perfectly elastic collision. Naming convention number 2 calls this perfectly elastic. I'll put the word off there. Naming convention number 2 calls this an elastic collision. I'm not convinced that the thicker letters are easier to read. I'll get to me in a moment. If kinetic energy is lost, so my initial kinetic energy is greater than my final kinetic energy, so I lose energy, but not sticking together, not sticking. Under naming convention number 1, this is called an elastic collision. Under naming convention number 2, it's called an inelastic collision. If they stick together, so my initial kinetic energy is greater than my final kinetic energy, and they stick. Under naming convention number 1, this is called an inelastic collision. Naming convention number 2, this is perfectly inelastic. Now, each textbook will pick one of these 2 conventions typically. I deal with way too many textbooks over the years. Some terms come in and out of fashion, but I hope you can see the confusion here that if I just say it's an elastic collision, which one are we talking about? Or an inelastic collision, which one are we talking about? I can't keep it straight through all the different textbooks. So I came up with my own, because you can't have too many naming conventions. So what I decided to do was, we'll take the unique ones. Perfectly elastic collision, that's what I call this. Perfectly elastic collision. Or as I will sometimes abbreviate, PEC. Under the sticking together, I take the unique one, perfectly inelastic collision. Or I sometimes refer to it as TIC. And then this middle one, which, according to some is elastic, and according to others it's inelastic. The people here are going, well, they bounce, so it's elastic. People here are going, well, we lost energy, so it's inelastic. The student came up with this one, and I liked it. Imperfect.
Elastic collision, or just imperfect?
Just imperfect.
Just imperfect.
And then the other category, which I think I mentioned last time, if the initial kinetic energy is less than the final. In other words, we gain kinetic energy. Textbooks typically call this impossible. And I call it flow arrest. Now, it is possible to gain kinetic energy if you throw, say, a bomb in it. I mean, fireworks, you shoot the fireworks up, it will explode, you are gaining kinetic energy. So in a situation like that, that's just basically the reverse of this. So the explosion is, it starts out together and then ends up in parts, as opposed to starting out in parts and ending up together. Questions before we double the number of equations we have?
Let's double the number of equations.
I think we'll ease in slightly today than I usually do. All right, so let's move on to chapter 8. 8, 9, and 10 I sort of lumped together.